Okay, this is a thermal question, 2007 AP question 2. The following questions relate to the synthesis reaction represented by the chemical equation in the box above. Again, remember, synthesis is when two elements come together to make a compound. So this is the most stable state of nitrogen, most stable state of, and then they gave you delta H and delta S. The following questions relate to the synthesis reaction. Okay, calculate the value of the standard free energy change. On your worksheet in there, it says right here, delta G naught. That didn't drag into this smartboard. So we're solving for delta G, and so we know delta H, we know delta S, so this is a pretty easy problem. Gators are hell without tartar sauce. We're looking for delta G because that's what free energy is, delta G. And so this is negative 264 kilojoules per mole. Remember, new notation, you're going to see mole RXN. I'm going to introduce it here, but you won't see it in the scoring guidelines. The temperature is 298. That's what this means. This little knot symbol means you're at standard temperature, and thermal is room temperature. So this is 298 K, that's T, and then S is negative 278 joules per mole K. And then the interesting thing that happens here is you can't have kilojoules per mole RXN and joules per mole RXN, because one of the rules is you can't add numbers if they don't have the same unit. So there's 1,000 joules in a kilojoule. And when I did this, negative 264 kilojoules per mole RXN. Keep in mind, this mole RXN, you won't see it in the scoring guidelines. A negative and a negative is a positive. This has 3, this has 3. This is a definition. So on this one, I got 82, positive 82.8 kilojoules per mole RXN. Again, you'll see just kilojoules per mole. All right, now when I add these together, I get negative 181.2 kilojoules per mole RXN. However, this has no decimal places. This has 1. You get no decimal places. So best answer is this, negative 181 kilojoules per mole or mole RXN. If you have this one, you'd be fine, because the new rule is you just have to be within 1 sig fig of the answer. Determine the temperature at which the equilibrium constant is equal to 1. This is a crazy thing. So one of the things we need, and I don't even think you'd see one like this anymore, but gators, and I'm dropping the circle, even though they took non-standard conditions off. Here's the thing that's interesting. Gators, and we're not going to assume that it's a 298 because we're trying to find it. Sorry, not gators. Girls are not real tough when they're having kids naturally. Now, the reason I grabbed this equation is because they told you that Kc is equal to 1. And so what happens is, on this equation, delta G is equal to RT, I'm not even going to take the time to look them up, ln of 1. Well, the natural log of 1 is 0, because any number except 0. So any number be not equal to 0 to the 0 power is 1. So the natural log of 1 is 0. So the question is, this is what you got to understand, that when Kc is equal to 1, G is equal to 0. So now the question is, and it's independent of temperature, there is a temperature at which, let me go back and just talk about this. Because here G is a negative 181, delta G is negative. That means at this temperature, this is spontaneous. But if you remember your box stuff, which is one of the most important things on the AP exam. So let me just, let me add a page here. You don't have to do this, but we talked about this a lot in thermal. So here's my box. I make a tic-tac-toe board. And so we have delta H, I'm sorry, you should put H on top. Delta H is negative, delta H is positive, delta S is negative, delta S is positive, and we know that nature likes exothermic reactions that get more disordered, so this is always spontaneous or spontaneously not spontaneous, thermodynamically favored. Endothermic reactions mean it doesn't happen on its own. You got to put energy in, and it's getting less disordered. This is never spontaneous, and then this is spontaneous at low temp, and this is spontaneous at high temp. So positive, and then here's the thing. So if you look at this problem, if you go back to the beginning, these are both negative, and there is a temperature at which this will go from being spontaneous to non-spontaneous, and this question is asking that question, where does that happen? Well, delta G is 0, because delta G has to be 0 if the ln of K is 1. And then, and the question is, where is the temperature at which this flips? Well, I'm going to bring this over here. T delta S equals delta H. And then I'm going to divide both sides by delta S. And so there is a temperature at which this flips. H is, if you go to the top, it is negative 264 kilojoules per mole RXN. You won't find the mole RXN in scoring guidelines. S is downstairs. And so I'm in a negative 278 joules per mole RXNK. And then this cancels with this, but kilojoules doesn't cancel with joules, so we have to know that there's 1,000 joules in a kilojoule. And this cancels this, and this cancels with this, and the only thing that hasn't canceled is Kelvin, which is good because we're solving for temperature. And so we find that the temperature at which this flips is what comes off on the calculator when I did it was negative 949.6 K. And this has 3, and this has 3, and this is a definition. And so the scoring guidelines say this with a dot there because that makes it 0 significant. That's a crazy way of doing that problem. Okay, I just did that. Calculate the standard enthalpy change that occurs when a 0.256 moles of NF3 is formed. Again, 1 atmosphere and 298 are standard conditions. So back to the equation. I'm going to rewrite it here. N2 gas plus 3 F2 gas goes to 2 NF3 gas. Sorry, gas. I did not mean to do that. Sorry. And then interesting thing, they told you that delta H naught is negative 264. It says kilojoules per mole. On the new test, it will say mole RXN. So I'm just introducing that notation. And the question is, if you have 0.256 moles of this, what will this be? And so this is just a strike problem. So and this is in moles, so we don't need to convert. So we have 0.256 moles of NF3 is the given. And the mole is the most important unit in all of chemistry. You're already in moles. And so the equation shows that for every 2 moles of NF3, see how there's a 2 there, you have 1 mole reaction. So this is the reaction as written. So this negative 264 only applies if this is a 1 and this is a 3 and this is a 2. And then we know that it's negative 264 kilojoules per mole per 1 mole RXN. This cancels this. 0.256 times negative 264 divided by 2. The calculator says negative 33.792 kilojoules. And because this has 3 sig figs and this has 3 and this is a counting number, best answer is negative 33.8 kilojoules. Fabulous. How many bonds are formed when 2 molecules of NF3 are produced according to the equation in the box above? That's way at the top. So the question is, and this is leading you, you have NF3. So let's just do, this is a bonding formula. It's always good to draw the picture. So N, and then you got F, and you got F, and you got F, and then this has 2, it wants 8. This has 2, it wants 8. This has 2, it wants 8. This has 6, it wants 8. I do ORP, and I get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So ORP is 26, and then VE is 5, because nitrogen's in group 5, plus 7 plus 7 plus 7, because fluorine's a halogen, it's in group 7A, and 21 plus 5 is 26, which makes sense. Well, what means this picture is wrong. And then, so how many bonds are formed when 2 molecules? So if you have 2 of these, 1, 2, 3, and then you have another one, 1, 2, 3, and so the answer is 6. Now, why is that important? Because we're going to use this weird equation, which is the fact that if I draw this picture, so N2 gas plus 3F2 gas goes to 2NF3 gas. So N2 is actually this. Trust me on that. Here's why. If I do N like this has 2, it wants 8. This has 2, it wants 8. ORP is 2, 4, 6, 8, 10, 12, 14. So ORP is 14, but VE is 5 plus 5, which is 10. We're 4 electrons short for every, so one line brings it down to 12, and the other line brings it down to 10. So 2, 4, 6, 8, 10. This guy has 8. This guy has 8. F2 is this. Here's why. This guy has 8. This guy has 8. ORP is 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12, 14. So on this guy, ORP is 14, and VE is 7 plus 7, or 14. And so that's the picture. And so, and then we just drew this. So let me just extend this page. And so what we have is we have this nitrogen molecule, and then we have 3 fluorine molecules, because it means moles, but it also can mean molecules. And then they come together. So this bond breaks and these bonds break, and then it comes together and reforms like this. But there's 2 of those. Now I'm going to do a new page, and then I'm going to come back here and go back and forth. So here's the deal. Delta H of the reaction is equal to the sums of the bonds broken. And which things break? The reactant bonds break, and then the guys swap partners, and then new bonds are formed. And so bonds formed, which are the products. And so an interesting thing happens here, and I'm going to go back to the notation. Negative 264 kilojoules per mole RXN is what the problem tells you that the delta H of the reaction is. Okay, now going back. 1 nitrogen-nitrogen triple bond is broken. Again, this is, they're not using the new notation because that didn't come up till 2014. And this is 2007, but I'm introducing it. So the nitrogen-nitrogen triple bond is broken, and 3 fluorine-fluorine triple bonds are broken. And so what happens is we have 1 nitrogen-nitrogen triple bond being broken, and that's 946 kilojoules per mole Rxn plus 3 times X. We don't know what this bond enthalpy is. It's a question mark. That's what we're solving for. What is the average bond enthalpy of that bond? But then we have to subtract the bonds formed. So there's 6 NF bonds formed. And wrong way. That is 272 kilojoules per mole. By the way, these bond enthalpies are always positive. It always takes energy to rip things apart that are connected. So then 6 times negative 272 kilojoules per mole Rxn. You don't. Now, negative 264 kilojoules per mole Rxn equals 946 kilojoules per mole Rxn plus 3x minus 1632 kilojoules per mole Rxn. And there is a rule in chemistry that you never, algebra, that you never work across an equal sign until you've simplified. So this and this are constants. We have to put those together. So negative 964 kilojoules per mole Rxn equals 3x minus 686 kilojoules per mole Rxn. Now I'm getting ready to solve it. I'm going to add 686 kilojoules per mole Rxn to both sides. Remember, there's a rule that you can't add or subtract numbers if they don't have the same unit. So this side is 3x because these are gone. And negative 264 plus 686 ends up being 422 kilojoules per mole Rxn. And then to solve for x alone, you'd multiply both sides by a third. And so then x is, my calculator says 140.6666 repeating. Infinite, we don't get infinitely many sig figs, we get 3. So best answer is 141 kilojoules per mole Rxn. And that is the answer.